In this video, I want to go over how you can implement temporal similarity search in KDB.AI. Now, there's two ways you could do this. You could implement this with transformed temporal similarity search and with non-transformed temporal similarity search. And transformed temporal similarity search has a lot of similarities to just using a regular index by breaking your time series data into windows, inserting that into a regular index and searching. And non-transformed TSS is a little bit more robust, but each method has its own advantages and disadvantages. And the best way to understand those is just to look at the code. So let's see this notebook here. And the first thing we're going to do is we're going to install the KDB.AI client. I've already done that step, so I'm just going to skip it. And then next, let's import our dependencies. And let's import some data here. Let's also ignore warnings because we live on the edge. And let's instantiate this function to gather some data about how two different methods perform. I've already set my API keys, so I can just instantiate my session. Nice. Let's look at our databases and see what we have. Okay, we have a few databases. I already have my database set, so I'm going to delete it. And then I'm going to create it again. Now, let's get our data and turn that into a data frame. Let's view this data frame. Okay, we've got some timestamps. We got some symbols. We got some quantities. We can view this as volume. And we got some prices. Now, what we're going to do in this notebook is we're going to compare two methods. We're going to compare simply windowing our data and inserting into a regular index. In this case, it's going to be a flat index. And we're going to compare that to using TSC. So TSC, or time series compression, compresses our data. So we get better latency and we use less memory. So it's very similar to just using a regular index, but we get the advantage of massive memory savings. So let's try this in practice, right? The process is going to look very similar for both. Here, we're just splitting our data into, we can think of them as chunks or vectors of size 1,000, so 1,000 dimensions. So we're going to group by symbol, and for every symbol, we're going to extract time, and we're going to extract the sliding window vector. And these sliding windows are something like this, right? So we have our data over time. This data is a little different from the data in the notebook. This is price change over time. In the notebook, we have price over time. And then we just create windows. This is a window of size n equals 3. And yeah, like we're just going one by one and defining windows of this size, right? And then we could search these. So let's go back to our notebook. And here, we've defined our windows. So let's look at this vecdf. What we see is that we have a bunch of windows. For every single symbol, we have windows. So this is window 1, and now we have window 2 that starts here, and that's right here. So we have an offset of 1 between windows. Now let's define our schema. So this is going to be just a regular schema. We have an index, we have a symbol, we have time, we have price. And now let's define a raw index. And we call it a raw index because we're not using transformed temporal similarity search. We're just using a regular flat index, which is going to do a brute force search of our vectors. So here we have a column that's price. We're going to use L2 celerity. And of course, our dimensions are going to be 1,000. And in both of these examples, this is kind of hard coded. So you can't make a query with 768 data points or 300 data points. That's one of the disadvantages of both these methods, both a brute force search and a transform TSS search. You can't really change this, right? But in this case, let's define our dimensions and our indexes, and let's create this trade raw table with a regular flat index. Now, you can use in practice, you can use an HNSW index. You could use whatever index you want with both these methods, because really, we're just inserting these vectors into an index. And the only difference with transform TSS is that we're compressing them as well, right? So, okay, now let's insert them into our table. This is going to take a little bit of time. Even though a flat index is fast, it's still going to take a little bit of time to actually insert into our database. So I'm just going to wait for a bit until this is done. All right, it took around 2 minutes, but we've inserted all of our data into our flat index. And now let's create a query vector, right? This query vector is just going to be the first 100 vectors in price. Sorry, first 100 points in price as a vector. And we can actually plot it and look at it. So this is what our query vector looks like. And our query is just price over time, right? And now let's actually make a search, okay? And we're taking account of the memory usage because we're going to look at that later. And what we get is, well, the first vector is exactly our query vector, and that's exactly expected, right? Because that perfectly aligns with our query vector. It's the exact same thing. And the distance is 0, right? Which makes sense. Now, the other vectors are around this area. So we have, this vector right here is number 3. And yeah, just vectors in this area. And this makes sense, right? Because, hey, like the most similar vector to this is probably a vector shifted a little bit to the right. Okay, so yes, we're getting a lot of similar vectors in the same space, but the idea is that we're returning enough vectors that we could actually create a little buffer and make sure we're filtering out identical vectors, right? And the result is we find vectors that are exactly the same as this, or like very similar to this, not exactly the same, with a similar shape. And that's very useful in practice, right? Because if there's a vector of a similar shape that gives us information, well, something very similar happened during that time. And then we could try the same exact thing with transform temporal similarity search, right? So let's define our TSC schema. It's going to look exactly the same. And our index, well, our index is also going to be a flat index, right? But here, we're specifying that we're using transform TSS, right? So here, we're using type TSC. If we look above, when we were inserting above, it was a little different. We weren't specifying that we're using type TSC, right? So that's the difference. That's the only difference here, right? Okay, so let's make sure to run this. And let's create this table. And then once again, we're going to actually insert the data into our TSC table. And this is going to take a little bit of time as well, so I'm going to fast forward. All right, so the data has been inserted into our TSC table, and it took around the same amount of time as the flat table. So, sorry, the flat index. And now let's run a similarity search. It's really fast, low. And we're getting very similar results. So once again, we have the exact same vector. The result is the result. Actually, is it the exact same? It starts at 20.18 and here. So it's the exact same vector. So that's basically our sanity check. We know that it's working correctly. And then we're getting pretty much the same results, right? But we're getting it much faster. So we see that there's a little bit of a distance, but if we actually look at this exponent, we see that this distance is negligible, right? And that's because TSC compresses. So suddenly the exact same vector can have a distance because we're compressing it, right? When we're actually inserting. And now the fun part, let's do the search evaluation, right? So what was the difference in search times? Well, okay, for our raw index, it took 1.3 seconds to search. For our transform TSS, this took around 900 milliseconds. So it was definitely an improvement, but this improvement increases as the size of our data increases. Now let's drop all these indexes and move straight onto Transform TSS. And this is going to be very similar. Notebook. We're just going to install the KDB.AI client, download our data, import our dependencies. Now let's make sure that we're once again living on the edge and we ignore warnings. I already have my environmental variable set, so let's connect to the session. And we're going to do the exact same thing. We're going to read this data. We're going to create a database. In that database, we're going to create a table. And to do that, we have to define a schema. And the schema is going to have an index, time, symbol, quantity, and price. And now let's create our table with a schema. Let's look at this data frame that we inserted. Okay, and let's insert this data straight into our table. So we have it sorted by symbol. We have like different quantities, which is like trade volume, and then we have price. Now let's actually run a non-transform temporal similarity search. So we've inserted all this data. That was really fast, by the way. It's non-transform TSS is very fast to insert data. Much faster than transform TSS. If you notice, like, look at this. This was instant. Just inserting our data. How long did it take to insert? Well, 0 seconds to insert 50,000 rows. Not bad at all. Now we're creating a query vector. And here, like, it looks like we're doing windows, but we're only doing this to get one window. So it's like, this can be done with less code, but hey, like, it's simple. Simple. Sorry. I'm recording this at very early in the morning or late at night, depending on what you consider it. And at this point, my brain no longer can tell the difference between symbol and simple. I'm going to edit this out. Anyway, so we have our query, and let's actually look at our query. It looks, well, it's the query from earlier, isn't it? And now let's make a search. Well, the search was fast. And we're going to check how much memory it's using later. And this is our result. We basically did an exact search. And let's look at this a little closer. The 100th index is the closest. And we have the price. And the distance is 0 for our vector, right? And then we're just like going by index here. So index 100 is very similar to index 99, which is similar to index 101. And that makes sense, right? All of these are going to be very similar. But let's actually, instead of getting 10, let's get 100. Okay. And now we're getting some very different indexes. So that's why a buffer is so important, right? So we're not looking at the exact same vector when we're searching. But, you know, we pass the sanity test, which is the 100th vector is the one we search with. And we can also do outlier search. Now, when we do outlier search, what we don't do is we don't try to find the farthest possible vector from the one we have. And this is what this code right here does. We have n is negative, so we take the 10 farthest ones from our vector, and these are just like as different as possible from this query vector. But that's not what an outlier is defined by. An outlier is actually something completely different. An outlier we could think of as a similarity search. So let's say we take a similarity search, and the first vector we get outside of our buffer. To see that, let's do 20. So we have a little buffer here. These are pretty much the same vector. And then finally, let's take 30. And finally, we get a result outside of our little bubble. Like, let's say our buffer is 10, we get 114. Or if we want to define a buffer to be greater, then let's go straight to 100. And then we get this result here, which is very different. Well, in that case, we look at how similar this is to our query vector. And if this distance is high enough, if this like the closest possible vector to our query vector outside of our buffer is different enough, that means that our query vector is an outlier. Just think about it. Like we just looked at the most similar data points in the data set, and the most similar thing is very different. That means the thing that we searched is an outlier. Now, how do you know what an end distance, what distance is large enough for you to consider something an outlier? Well, you can do this statistically. You compare every vector to every other vector, and by that, based on that, you create basically a statistical variable to tell, hey, like what is the criteria of something being different enough based on our distribution of data? Or you can adjust this and say, hey, like typically based on like this distance, if it's that different from our query vector, that seems to be an outlier, and you could set your own criteria. So this isn't exactly outlier search here with n equals -10, but it does bring us the most different vectors. We can also change the size of the data points, and that's a major advantage. So before we were searching 100 data points, I think, and now let's do a dynamic search where we're going to search only 50 data points. We get different results. Hey, like for 50 data points, our third vector is actually pretty different. Sorry, our fourth result. So we get completely different results if our query size is different. And we can also do it with a 500 element vector, and we get completely different results as well. So the vector we're searching is different. So of course the results are different. And this isn't very easy to do with if we're using windowing, because if you have a window, you define the windows, and then you're basically stuck searching with that window. Here we could change the window size for its time, so that's very convenient. You can also make multiple searches. So here I'm searching, a 50 vector query and a 500 point query, and I'm getting lots of results at the same time. And now let's do our evaluation. So we're using very little memory. So our memory looks good. And let's look at our search timings. So, whoa, this is very fast. Only a couple hundred milliseconds. Now finally, let's draw our table. So I really hope this video helped understand the differences between transformed TSS, non-transformed TSS, and just using a regular index in order to do temporal similarity search. Also hope this helps understand what exactly is an outlier and how transformed or non-transformed TSS can be used to find outliers. And that's it. I'll see you in the next video.